right, folks, so we are moving into the statistics lesson and the probability module, statistics and probability module at this point. And I want to check in with everybody before we move into this module. And as we do, we start with the overview and then we get into the details. What I'm doing right now is sharing a link in the Zoom chat to a Google Doc where all of y'all have permissions to write to this. And what I'm interested in here, give yourself a little space to type. So hit enter a whole bunch of times so you can get your own line. What I'm interested in here is your feelings and thoughts and what comes to mind when you hear the terms probability and when you hear the term statistics. There's no wrong answers here, and I see lots of anonymous animal names, so feel free to be as completely honest as you can be on this one. Please, it will help the process. I love seeing a dozen plus people, like almost 20 people typing out. Yeah. This is cool. And let it all out. Let it all out. This is therapy. If you've ever had any crosswise feelings about probability or statistics, this document is therapeutic. And it's anonymous too. Like, I think the only non-anonymous accounts on here are if you have a CodeUp account. So anonymous mammals of all kinds are telling, oh, there's fruits and vegetables too. That's cool. Yeah, let us know how you're feeling. This is a really, really valuable for us. And it's valuable for you. Share your feelings, get it out. Thank y'all for sharing your thoughts and feelings and some fears too. Right? So looking at this one, I think y'all are, I'm collecting information, right, from a group. I'm surveying a group. So um, we're getting a lot of thoughts here. Russian roulette. Yeah, there's certainly probability and statistics in there. Yeah, Vegas, absolutely. The house always wins, right? It is what they're trying to set up. And when we get into some of their simulations, we can talk about how to make fair or unfair simulations. Interest combined with an irrational fear. Wow. The lottery. Need to practice to get better? Yeah, absolutely. We'll be doing tons and tons of practice with our stats and probability work. And then we'll also be tying in the tools that we work with in this module to everything else we do the rest of the course. So this isn't one of those modules where we do it a week in probability and then we expect that you've got it, right? We're going to do this module in probability and stats, and then each project and each data science project from here on out, end-to-end data science project. I think there's like one or two that don't have hypothesis testing, but they all have some statistics in them somewhere, right? Looking at the distribution of values or measures of central tendency or measures of spread, right? Yeah, hard to know where to start sometimes. Dread, yeah, these are real things, real feelings. Like, and right now I'm surveying folks who signed up and are doing everything in their world possible to become data scientists, right? Where you already know that there's going to be a lot of stats involved from the definition: math, stats, programming, and business and domain expertise, right? So of all the audiences on the planet, I'm expecting, like, we all have different feelings, right? Some dread, knowing that we need some practice, hard to know where to start, numbers and percentages, risk analysis, different distributions, absolutely. We will do some coin flipping problems that are deceptively simple. The goal is not to deceive you, but the goal is to have something simple to start. I want to know more. Boy, I like that one a lot. Me too. I think I'm never done learning new stuff, learning new things in probability and in statistics, right? Oh, marbles in a bag. Yeah, we've got marbles in a bag, coin flips, lottery. Actually, one of our students from Darden, Angel Gomez, made a lottery simulator. He went and got the percentage chances off the back of lottery, like scratch offs, and built a like a Python simulator. Pretty cool. It always sounds the easiest, man. Cool. And then we've got some modeling, regression, p-values, significance level with a question mark, data. We've got some different statistical tools. What we're going to be doing in our neck of the woods here is we will be doing all of our probability work and our simulation work and hypothesis testing. All of our stats we're going to do in Python. So I think it's very nice and refreshing that we don't have to learn a second tool on top of this. We can take all of our Python chops and completely integrate them holistically with your stats and your probability chops through this module. Not always sure how to approach a problem? Cool. We're gonna talk about how to break that down and get into that. Yeah, biomedical, epidemiological statistics, probability, Vegas, blackjack. Yeah. Predicting the weather. Yeah, stock market. Yeah, stats was one of my hardest classes in college. Okay, you're probably not alone on that one. I think I've heard that one before from past students. Yeah. It's been years, but I know I can relearn it. I agree, you can relearn it, especially with how we approach it. And then some more vocabulary words: sampling, modeling, p-values, confidence intervals, regression. Good. Heart of Gold and the Infinite Probability Drive. I think that's from a bit of fiction that I haven't personally read, but that sounds cool.
It's a Checkers Guide, if I'm not mistaken.
Yeah, I think that's Zaphod Beeblebrox or something like that.
And just remember what the book says. Don't panic.
Easier said than done, right? Especially if we're talking about statistics and probability. Summation notation, not a fan. Wow. Okay. If you were like bleh when you see a big fat Greek sigma and summation notation, have I got news for you? Python is going to make you very happy that you have a programming language. Very happy. Because the summation notation, y'all already know how to do that in Python. You just write sum. You know? And if we need to sum something that has like a list where there's a whole bunch of stuff going on, like if like sum up only the even numbers or something like that, well, guess what? We can put a list comprehension in a sum, or make a variable that holds that list comprehension, filter the list and put it in a sum. Delight in making statistics easier. I agree. I think an angel gets its wings every time a human being is able to explain to another human being something statistical or probabilistic in a way that they understand, in a way that's actually accessible to the listener, right? Yeah, likelihood of outcomes happening, a way of describing trends in data, RStudio, MATLAB. Yeah, those are really powerful. Fear and complex algorithms and formulas. Okay, cool. These are real and valid feelings, right? And y'all are a very interesting population, right? There's not a lot of populations that look like this class in terms of the skill sets y'all are bringing in, the desire, the motivation, right? And then I'll share my own thought and feeling on statistics and probabilities, specifically books. I feel like every stats book or probability book that I've ever picked up, they all have the same like first chapter, maybe second chapter, but by chapter 2 or 3, it's all they're all going their own path. That's just been something I've noticed, because every author seems to have a different way of explaining it that they think will get through. That's at least my own experience, and that I'll share. It just to make that a reality for y'all, this approach that we cover in CodeUp will be completely different than anything you've seen in the stats class before. Most likely, unless you have a stats class written in Python and Pandas that is simulation based first before getting into the theory. Cool. Thank y'all so much for sharing your feelings. Like, I think out of all of the topics that we cover in data science and in the course, I don't think people freak out so much about like Python or SQL as they might freak out about stats, right? So we're taking a different approach, and I want to acknowledge these feelings, like acknowledge it's almost like there's a combination of hope and fear. I feel here. Like I see messages of hope, like, oh, I know I need to practice, but it's powerful. And then literally the word says dread, another word says fear. Right? So we're going to take a different approach because we're able to do things with Python and integrate things with Python. So I want to acknowledge that right now. That's the thought for the day. We're going to calculate probability. We'll calculate probabilities by blowing off statistics. That is our goal today. And we will get into some statistics later. So let me share my screen and we'll get started. So looking at where we are and what we're doing, so that y'all are tuned in and oriented and have your bearings, we finished up the storytelling in the Tableau. We're starting the stats module. And everything after stats, all of the methodologies 1 and methodologies 2, everything from here on out will be the module is you learn basically a new machine learning tool or a new data science methodology, and then we do a project in it. When you learn a new tool, we do a project in it. Learn a new tool, do a project in it. And almost all of those projects, maybe 1 or 2, Actually, all of them will have some sort of statistical approach, right? In fact, all of them. So what we cover in this stats lesson, we will review and reinforce and repeat, review, reinforce, repeat, over and over and over. Okay. So roadmap for what we're going to be doing right now, folks, I'm going to go over this overview, and this will be our high level overview. And I'm going to set the expectation, expect that by the bottom of this page, you will see some summation notation. You will see a capital sigma. But that's only because this particular page in the curriculum doesn't have any Python code on it. We will introduce the Python code in the simulations lesson, that's actually like a lesson with an exercise. This overview is just kind of an overview, 10,000 foot overview. Okay. So let's jump right in. It is definitely the case that there are 3 types of lies. I agree with this statement. Lies, damn lies, and statistics. And I think this comment from Disraeli, and I've heard this attributed to a lot of folks. I think this is speaking to something we all know and feel, that statistics can both clarify and muddy the issue, right? So from my personal perspective, the more we know, the more vocabulary we have, the more our concepts are just founded and rooted and rock solid, then we will less easily be lied to. If somebody is tossing around the word statistics, throwing around summation notation, trying to stress you out so they can make a flimsy crap ass argument, right? Because that happens in the world. So we'll talk about some of our basic descriptive statistics, and all a statistic really is a measurement, right? Like a batting average, or gosh, even like a bowling score. The score is some statistic. There's a certain set of rules for measuring a bowling score, right? And we talk about averages, and we talk about mins and maxes, that kind of stuff. We'll talk about different kinds of probability distributions. And when we talk about distributions of probabilities, we're looking at, like, what is the shape of the outcomes? What do the shape of the outcomes look like? When I say shape of the outcomes, like flipping a coin, we should have only 2 outcomes, right? And then we'll get into the second half of this module will be hypothesis testing. So we'll start with simulation later today, maybe this morning, maybe this afternoon, probability distributions, and then we'll get into hypothesis testing, where we find ourselves in the business of trying to disprove things, right? Trying to disprove things, so that we can more clearly understand what's left over after we've disproved things. All right, our goals here. The goals that we've got for everyone here, build on top of the knowledge that you got from either the Khan Academy pre-work or any experience that you've already had with anything probabilistic or statistical related. We want to build on top of that key understandings that we need to be able to walk away from this module knowing is the difference between different kinds of distributions: uniform, binomial, Poisson, which it's fun to say. Say it with me, say Poisson, Poisson. We will talk about Poisson distributions and normal distributions. And so we'll see a lot of different shapes of probabilistic distributions. And then we will talk about hypothesis testing. And you will do lots of hypothesis testing. We will introduce a couple of different kinds: t-tests, correlations, and chi-squared. And the big thing that we'll be doing is we'll be writing Python code that simulates experiments in order to calculate experimental probabilities of things. This is very nice because we might have real world data where we can create a simulation that mimics that, right? And we might not know everything that there is to know about that problem, but we can at least model that world, model some process in the world in your Python code, right? If that process is cards or dice or coins, right? Or more business relevant questions like churn, right? Cool. We will introduce a couple of new, at least one new tool in this module, the SciPy Stats library. Okay, and this whole module is going to be all about Python code. This overview page is the only page in the stats lessons that don't have any Python code. Okay. There is going to be some visualizations throughout this module, and in order for y'all's focus to be on the stats and the probability and less on the matplotlib, we're kind of hiding away some of the matplotlib and Seaborn code, except it's accessible through this overview page. So there's a whole bunch of visualizations. I think there's like, I don't know, there's almost a dozen or more visualizations. To reproduce those visuals, the source code is over here, right? But we're not going to show off chunks and chunks and chunks of matplotlib code when the point is just doing the work, right? So that code is accessible from the link right here, where the link says here in green text. Okay, so we're going to look at some descriptive stats, and then I do want to find, let's see, yeah, let's cover some of these descriptive stats real quick, and then we'll get further and deeper into things. So we do have to build our more complex pieces on simpler pieces. So let's take a look at our super simple pieces here. When we talk about descriptive statistics, that term means to use descriptives, to use certain statistics to describe what our data looks like. And the first kind of family of measurements, and that's really all a statistic is. A single statistic is a measurement, right? So we can have all kinds of measurements. Well, let's look at measures of central tendency. Central tendency is a fancy way of saying, what is the middle? What does most of the data look like, or what does the middle of the data look like? There's a couple of ways of answering that question. We have our mean, which, oh my gosh, we have summation notation here, right? But the mean is pretty simple in pandas. You do dot mean, right? On a series. And the mean is the same thing as the arithmetic average, the plain old average, right? If we had, if we needed to calculate the expected value of something, it's similar to the average, except that each value is weighted by its probability of occurring. So it's, this could, with expected values, we could model an unfair coin or a fair coin, fair dice or unfair dice, right? The median is another measure of the center of our data. So rather than getting an average of everything, with the median, what we do is we put all of the numbers in a series or an array in ascending order, and then we look at their position. How many numbers do we have? And let's look at the very middle number with the median. So the median will be the middle number if we have an odd amount of values. So if we had 3 values on a list, the median is the middle number, right? What if we had 4 values on the list? Well, if we have 4 values on the list, the median is the average of the 2 middle values based on their index in a sorted array or a sorted series. So median is pretty kick butt, right? Because median is not quite as sensitive, not nearly as sensitive to crazy outliers, high or low outliers, as the mean. So if you're doing a salary negotiation or something like that, my advice is to ask what the median salary for the role is, or at the company, rather than the mean. Because if the CEO is taking home 100 times what everybody else is, that 100 times pay is going to skew the mean, but it won't skew the median. Not quite so much. right? I digress. I digress. So median's really valuable for us when the data could have high or low outliers, right? It's a good measure of the middle. The mode is our most frequently occurring value, right? And all of these are methods on a pandas series, or just mean, median, mode. If we have two modes that tie for the most frequent, then we have a bimodal distribution, and that might look like a camel hump if we plot out the distribution. It might look like a camel hump. It would look exactly like a camel hump. Okay, so this is kind of interesting. And right here, when we're talking about measures of central tendency, there's not one measure of central tendency. And in fact, like when we look at expected value, or we look at mean and median mode, these all share a different lens on the data. But one of these measurements is not the whole story, right? So this right here, having multiple measures of central tendency, and there's not like a mathematical answer to which one is always the one you want to use, right? I think right here at the measures of central tendency, we're seeing where there's ambiguity, there's judgment calls, right? There's we've all seen outfits that advertise average when they as a way of trying to advertise their extreme outliers, right? So this is just right here at the measuring what's the middle of our data. We don't see the whole point with only one measure, right? Cool. And I think that speaks to why folks have a feeling of, okay, statistics is powerful, but it can also be used for evil, right? It can be used to obfuscate the point as well as to show the point. So let's take a look at some of our measures of spread. And all spread means is where our values are, how far the values are apart from the middle. Min, max, go figure what those are. The range is the difference. And then we introduce this concept of a quantile. And a quantile it's a cut point that divides up probability distributions into equally sized chunks, right? So when we talk about the median is a really good example of a quantile. It's a cut point that cuts our data into two chunks, above the median and below the median. And the median itself is that cut point, is that quantile. Okay, so we can have all kinds of different cut points in the data to look at chunks of data, as opposed to each and every million different data points with very finite precision. We can kind of group things together. So a median cuts the data into 2 points. Other kinds of quantiles we can break into 10. We can break our data into 10 buckets. We can break our data into 5 buckets, 4 buckets, whatever is useful. So quantile could be any kind of bucket, any size bucket. And the idea with a quantile is that these are equally sized chunks. Let's look at a concrete example of that. Building on what we saw with the median is the middle of our data point, and it cuts the data in two. Something that you're going to hear very quite frequently is a concept of a quartile. So a quartile is 4 chunks, 4 quantiles. That's where the quart for 4 comes in, right? Like 4 quarters. And what we see with the quartile, we have 1, 2, 3, 4 chunks of data, 4 buckets. And with those 4 buckets, we have 3 cut points. The middle cut point we've already talked about. That's the median, right? Because the median cuts a chunk of data into two evenly sized chunks or intervals. And then so another word for median would be the second quartile, or Q2. Okay, it's just another word for median, because if we have 4 quartiles. So what's between the lowest value and the median? The halfway point between the lowest value and the halfway point is the 25% point, and that's called the first quartile. So we have a first quartile, which is the midway point between the minimum value and the median. We have the second quartile, which itself is the median, which is a single value that's the median. And then we have the third quartile, which is the middle point, or the median, between the median and the highest value. Okay. You might hear quartiles referenced in terms of like income distribution in communities or countries. And it's pretty useful, because if we have 1,000 different data points, we can break them into 4 chunks and look at are most of the values, where are they trending? What do they look like? Right. A percentile is all this is a quantile with 100 equally sized intervals, which just works out to be what we in normal English talk about as percentiles anyway, percentage points. So with a percentile, we have 100 points in a quantile. Something that we'll get to use a little bit more, especially when we work with outliers, is something called the interquartile range, which sounds really fancy, right? What did you learn at CodeUp today? Let me tell you, I learned about the interquartile range. Well, here's the definition of an interquartile range, and I'll give you the math definition second and the conceptual definition first. The interquartile range is trying to capture the most values. That's all it's trying to capture. And we might miss it. This might fence out some outliers. But what we're looking at here is the spread between the third quartile and the first quartile. Right? And that's a single number. Since it's a single number minus a single number, it gives interquartile range as a single number. Okay. All right. Let's see. Questions so far before I proceed. I want to make sure I'm not just going down a checklist too fast. I want to give you all an opportunity to ask any clarification on percentiles, quantiles, quartiles, interquartile range, measures of central tendency.
So that box and whisker plot really shows the IQR, right? Shows that spread. We use that.
Yeah. So let's do a box and whisker plot. This is a great question, David. Thank you. Perfect. We found a perfect diagram here for an interquartile range, and actually a box plot, right? So looking at our handy dandy box plot here, we see the median value is the line, and see how median is a single value. It's like maybe 0 or right near 0 in this example data set, right? The whisker to the left is the minimum, and this is this definition right here, this Q1 minus 1.5 times IQR. We will actually use this definition of a minimum and a maximum. See how these are not the actual minimum or maximum values, because we have outliers above and below them. We'll talk about that with outlier detection. But yeah, the Q1 is between the actual lowest value. It's the midway point between the actual lowest value and the median. The Q3 is the midway point between the median and the highest possible value in this data set. So yeah, the box part of a box and whisker chart, the horizontal width, if it's horizontal, is in fact Q3 minus Q1. And the visual is just killer here, right? And don't sweat this 1.5 times IQR. We'll get into this. It's an outlier detection tool that we'll cover a little bit later. Yeah, good question, David. Thank you. Or good observation, right? All right, cool. Other questions on what we've talked about so far, what we've covered so far? This is the part of the episode where I ask for questions and then we get the questions.
I think like the one that always gets me confused, and I like these definitions, is like the percentile. People will use like 80th percentile versus 20th percentile, or they'll say the upper echelon of the percentile. I'm like, oh my God, can you just tell me one number? And there's like multiple ways to describe it, but it's how they want to spin it. And it gets me so freaking confused. I hate hearing percentiles.
Fair. Yeah, that's fair.
Like absolutely what David said. I don't know if this child has a giant head or if it's normal.
Well, and is the range of 20 percentile to the 30 percentile, is that still normal? Like what is the center? What is, lots of definitions there, right? Awesome. So are y'all good on the interquartile range, percentile, quartile, quantile? And if we're having trouble with the min and the max, we should probably talk on Wednesday, or maybe over lunch. I mean, this might get kind of funky if we have multiple values that are all the minimum. They're the same, right? But we still have a minimum. All right, cool. We're making good progress, y'all. Let's proceed forward. So in what we've been talking about after the central tendency is how spread out is the data on a distribution, right? And when we're talking about a distribution, we're looking at how often certain values pop up, right? We've talked about, so let's talk about variance and standard deviation. So variance, oh my gosh, summation notation. We'll get this out of the way pretty quick and be doing Python by the next module, right? The variance is the average square distance between each point and the mean, which sounds great in a statistics book, but what the hell does that actually mean? Well, looking at the variance, if we're looking at the average square distance, we're not looking at the right measurement. So if our units are dollars, variance isn't dollars, right? If our units are inches, variance isn't inches. So what's very commonly used is taking the square root of the variance, so that if we are measuring something in dollars, we get our standard deviation in dollars. If we're measuring something in centimeters, we get our standard deviation is measured in centimeters. So we keep our units the same when we use the standard deviation. And all the calculation is the square root of the variance, right? So measuring the distance, right? This xi minus mu, this is measuring the difference between some given value in a list of numbers and the average of that entire list of numbers. Right? So all the standard deviation is doing is measuring absolute variability, which is just above the median, or above the mean, or above or below the mean, right? Cool. We're going to see standard deviation a lot. Great measurement. It's valuable to be able to talk about, the price is $10, give or take $2, right? Or somebody's height is 5'6", give or take 4 inches, right? The give or take here is the plus or minus the standard deviation. And when we were calculating z-scores, do you all remember we calculated some z-scores in SQL? A z-score of 1 means that an observation is 1 standard deviation away from the mean. A z-score of 2 means that observation is 2 standard deviations away from the mean. So that standard deviation is a single value, it's a single number.
So is that why we end up using standard deviation more than variance? Because it has like the same type of unit?
Yeah, it has the same unit, and yeah, it's quite a bit more common. Quite a bit more common.
Yeah, seeing those formulas, that just always brings up like my stress levels. And then when I get into, I'm like, oh, it's not that bad, but just I don't know why it is, just that the way they're written, just
Yeah. Well, do you want to would you like to see something refreshing, David?
I would love that. Yeah.
All right, cool. Let me make something refreshing for us here. I'm going to pull up my Easily, and I'm going to fire up a notebook here super quick. We don't need all of that. We don't need all of that. Let's make a list of numbers here, and let's make them a list of numbers between 1 and 100. So we can get, and then let's make a nice little series out of this one. So we have all of our NumPy tools and all of our Pandas tools in one place. So this shouldn't be too crazy. The minimum value is 1. The maximum value should be 100 because the range is exclusive of the upper bound. And so when we get it, remember we saw some sigma notation, that summation notation right here for the mean. Give me a break. Give me a break. I thought mathematicians wanted efficiency in notation. I'll give you efficiency in notation. It's dot mean. Right? So we don't need any capital sigmas or anything else. The median, right? We don't have to get into this and ask if we have an even number or an odd number of numbers. We just get the median. It's just very nice that these are the same in this specific data set, right? And then we can ask the standard deviation as well. So on average, most of the values in the data set of 1 through 100, most of the values are plus or minus 30 from the mean. This is how to read that. So what the standard deviation is telling us is we can get, most of our values are plus or minus about 30 from the mean, right? I think, remember if quartile is a method or if I have to do a quantile and give it the number of arguments. Yeah, that's how okay, so I'm gonna make some quartiles here, quantiles, so I can do 0.25. And this gives me the first quartile. And I'll be adding, committing, and pushing my notes for y'all. Right, so we have our first quartile, 25.75, and that sounds pretty good because we're talking about the list of numbers between 1 and 100, right? Our Q2, which is the same thing as the median, another way of quantile, what's the 50% mark? That's Q2, it's the same thing as the median. It is literally the median. Q2 is literally the median, always is. And Q3, x dot quantile 0.75 Q3. Great. Not too shabby. My goal here was to take a look at some of our summation notation or a sigma notation and say, hey, we got this, right? Do we want our interquartile range? Interquartile range is Q3 minus Q1. So our interquartile range is almost 50, which I think makes perfect sense if we have a list of 100 numbers, right? In order, all integers, positive integers between 1 and 100. What if we have a different variable? What if we have a variable called y? And it's just a bunch of ones. actually, we have just a whole bunch of ones, right? Well, if we take our average of a list of ones is 1. Our min and median are all the same, right? What, any guesses? Let's talk measures of spread. What do y'all think the standard deviation of this list of ones is going to be? Any takers?
Zero.
Bingo. It's because there's no deviation. We can't, for our standard deviation, if there's no distance between every value and the mean, because they're all the same thing as the mean, then we don't have any deviation. Absolutely. Absolutely. Cool. Was this a helpful just side quest a little bit?
Yeah, I love this side quest. More of them. Yeah.
Awesome. Yeah, it is my hope. It is my hope for y'all, and this is something so there's a way of writing math notation in code called LaTeX. It looks like it's spelled latex, but it's pronounced LaTeX. My hope is that the hardest part about summation notation for y'all the rest of your professional career is writing the LaTeX to make the notation rather than to actually do the math. Because doing the math, as we saw, is not too bad, right? Right? We just have to have the right function and the right libraries. Does that mean that we need to be critical thinkers and critical consumers and critical producers of statistical measures? Yes. But if there's any anxiety with when you see a big sigma, my hope is that the hardest part is writing the LaTeX that renders this rather than writing the code, right? That's my hope. Because LaTeX has a bunch of $signs and backslashes and stuff like that. So I don't want you to worry about that either. All right. Some other measures of variance and measures of spread are this concept of skew. And when we talk about skew, we're talking about is the data, when we look at a distribution of the data, is it going one direction or another? So let's see if I can't give us an example. When I look at a histogram of X, X is just the numbers of bins equals 100, right? We have 100 different numbers and they're all showing up once, right? But what if we had a variable that was like 1 1 2 2s 3 3s 4 4s 1 2 3 4 5 5 5s. So this is kind of a lumpy data set, right? It's not just the numbers 1 through 100. So when we look at a histogram of this, we see that there's a lot more values in one spot than the other, right? And so what we'll do here is we will say that if the distribution is not like a nice normal bell curve, we will say that the distribution is skewed left or skewed right. And my mental image for this, so let's see, when we are left skewed, the set of values when the mean is generally less than the median, okay? The left tail of the distribution is longer than the right tail of the distribution. So looking at this, this is pretty good left skew. Let me find another visual here. Skew examples. Perfect. So when we talk about something being left skewed or right skewed, and I'm totally gonna steal this image for the notebook. It's almost like we have what's determining the skew is if we have like a little gerbil or something under the curve, dragging the curve left or dragging the curve right. Is my mental image to keep this straight. It's like the little gerbil is running all the way to the right and skewing the graph to the right. And this is interesting too, because when we see a left or a right skewed distribution, we can compare that the mean, the median, and the mode are following mirror patterns. They're not the same numbers, right? Cool. All right. So at this stage in the curriculum, my encouragement, my words of encouragement here are if you can do like single variable algebra, solve for X kind of stuff, you can do and get step into the simulations exercises without, you don't have to have a lot of math theory in your background. Just at this point, you need to know your Python, right? And we need to be able to set up our code to reflect a real world scenario. And once you do enough simulations to get a handle of things, then we'll go into working with probability distributions. That's when we get to the statistics on a more theoretical standpoint. Like if we did an infinite number of simulations, for example, and if you can work with the probability distributions, then you can do hypothesis testing. So if you can solve for X in an algebra problem, we're not solve for X and Y in a more complicated setup, then you have everything you need to go through this lesson. So that's my takeaway for you. If you see summation notation and it's like, oh my gosh, well, guess what? Dot mean, dot median, dot STD for standard deviation. I think variance is dot VAR, right? Cool.
I don't know if this is too off topic, but I noticed that whenever you opened up your Jupyter notebook, it already had a code. How is that done?
I built a thing that generates an empty notebook with a whole bunch of imports already. I could share how to do that maybe at a time when we're not doing a lesson. I would be happy to share how to do that, just not in the middle of the lesson right now. All right. So that's our 10,000 foot view, 10,000 foot overview, right? We need to be able to measure what does the middle of the data look like? And there's handfuls of ways of measuring what the middle of a data set looks like. And then we want to be able to have multiple ways of measuring how spread out is the data. That's the punchline. That's what descriptive stats is. And in the real world, we see descriptive stats and even custom statistics used all the time, like batting average or earn base average, right? Or like consumer price index, right? Consumer price index, it's not a mean, it's not a median, it's like a conglomerate of all kinds of different measurements, but it's just one number to pay attention to. We see it all over the place, right? All right. Cool, folks. How y'all doing? How's everybody doing? I see the same number of participants in the call right now as we started with on the beginning of this lesson. So thanks for having the fortitude to face the statistic, to face the intro. Y'all up for a little break and then we'll continue with the simulations? Cool. We had our longer break already. How about 7 minutes? 8 minutes. We'll do 11:47. And we'll proceed forward.